Hello everyone and welcome to your lesson of physics. So this is the second video about the topic of electrical charges, aka static electricity. And this one I'm going to solve past paper questions, P1 and P2 questions. So let's start with the first one. Here we have two balloons X and Y are suspended by insulating threads. Uh, they are each held near a negatively charged balloon. The balloons hang as shown below. Let me just grab my pointer here. Okay. Then we can see there was a negatively charged balloon, and uh, we are hanging another balloon X in front of that balloon, and also in the second case, in front of the negatively charged balloon, we are hanging the balloon Y. What is the charge on balloon X and what is the charge on balloon Y? Now, first of all, you can realize when there was a balloon X in front of the negatively charged balloon, it appears that the balloon X is being pushed away, is being repelled by the negatively charged balloon. So that means the balloon X must be having like charge with respect to this balloon. So in that case, it must have been negative charge. Only then these two balloons will repel each other. So there must have been negative charge on the balloon. And when we were hanging the balloon Y in front of the negatively charged balloon, they were being attracted. That implies that the balloon Y must be having unlike charge. So it should have been positive charge over here. So negative on the balloon X and positive on the balloon Y. All right, that was a pretty simple one. So B is the right answer for this one. Then we have the next one. A plastic rod and a dry cloth are uncharged. The rod is now rubbed with the cloth and they both become charged. The rod becomes negatively charged because some of the particles move from the cloth to the rod. So rod is becoming, we have two things here, rod and cloth, and the rod is becoming negatively charged and the cloth would eventually be positively charged. So what is the charge on cloth and what particles and which particles move in the charging process? I mean, that's very straightforward. In my previous video, I explained this thing that all the charging in all the stuff has to be explained in terms of electrons. So whenever they say what particles move from one object to the other, one body to the other, it is always electrons. We always describe charging in terms of electrons. So two options they explain in terms of neutron, you can throw them out the window straight away. Then we left with A and C. A rod, like I said, they have written is negatively charged, so eventually the cloth would be positively charged. So charge on the cloth would be positive, particles that move would be electrons, and that has to be the answer C. So C has to be the right option for this one. All right, so let's move on to the next one. All right, so here we have the next one. Two similar balloons hang side by side on insulating threads a short distance apart. They are both rubbed with the same dry cloth and become charged. Which diagram shows how the balloons hang after charging? So two similar balloons mean they are made up of the same stuff and they are rubbed with the same piece of cloth, with the same, they're rubbed with the same dry cloth. So both, that implies that both the balloons must be getting the same charge. Why? First thing, because the balloons are similar, they're made up of the same stuff, and they are being rubbed with the same stuff as well. They are being rubbed with a dry cloth. So both the balloons would be getting same charge with respect to each other. And if they have same charge or like charge, they're going to repel each other. So in this case, if they're repelling each other, they would be pushed away from each other by uh, the same force. So C can't be the right answer because it shows that the balloons are being attracted. A shows there's no force at all, and D shows only one of the balloon is being pushed away. So when there is a force of repulsion, the force of repulsion is there on both the balloons and from both the objects, or from both the objects. So B has to be the right answer for this one. All right, now we have another one. A negatively charged plastic rod is placed above a positively charged plastic rod Q. Okay, rod P is placed above rod Q. P is negatively charged and Q is positively charged. What are what are the directions of electrostatic forces on the rod P and on the rod Q? Oppositely charged means they would try to attract each other. P would be pulled towards the rod Q, and rod Q would be pulled towards the rod P. So the force on the P would be downward, like you can see over here. The force on the P would be downward, and the force on the Q would be upward, because uh, there would be a force of attraction and they would be pulled towards each other. So from the perspective of P, it would be downward, and the electrostatic force on Q would be upward. Only then they can appear to come close to each other. So B has to be the right answer for this one. All right, moving on to the next one. Here we have, which group contains only good electrical conductors? All right, so a part of this topic, a part of the topic, or one of the topic of this chapter is the difference between the electric conductors and insulators. So we have to figure out, we have to select a set of objects that contain only good conductors. Air is not a good conductor, so you can discard option A and B. Plastic is an insulator. Once you try to pass electric current through the plastic, it offers so much resistance that it will start heating up and eventually start burning off. So C is the right answer. Matter of fact, carbon, when it's in the form of graphite, is the only non-metal that is a conductor. Copper and mercury, these two are very good conductors, and carbon, once in the form of graphite, then it's a good conductor. Moving on to the next one. A polythene rod is rubbed with a cloth. The rod and the cloth both become charged as electrons move between them. The rod becomes negatively charged. Okay, so negative charge appears on the rod and hence positive charge would appear on the cloth. That implies once you have rubbed them, electrons from the cloth would have moved towards the polythene rod. Only then you can have negative charge on the rod and positive on the cloth. So that has to be the movement of electrons once you rub these two objects. Alright, which diagram shows how the rod becomes negatively charged and the final charge on the cloth. So final charge, like I said, if rod is becoming negatively charged, then the cloth would obviously be getting positively charged. And which diagram shows how the rod becomes negatively charged, and final charge on the cloth. So final charge on the cloth has to be positive, so you can discard the option C and the option D, because these two options show that the piece of cloth is having negative charge. However, instead, the piece of cloth must be having positive. Now, so if the piece of cloth is having positively charged, it's positive only because the electrons from that piece of cloth move towards the rod. If you take a look at the option A, that says exactly the opposite. It says electrons from the rod move towards the cloth. Had the electron moved from the rod towards the cloth, then cloth must have been having negative charge. So B is the right answer, because B says, yeah, when you were rubbing these two substances, when you're rubbing these two bodies, electron moved from the cloth towards the rod. That's why the cloth was having positive charge, and that's only why the rod is having negative charge. Once again, moving on to the next one we have here. Alright, a polythene rod is rubbed with a cloth. The rod becomes positively charged. Again, we have two substances, rod and cloth. It's always good to write down the name of the bodies that are being contact with each other, and then you can just represent the electrons movement on them. The rod becomes positively charged. Okay, so positive here obviously would be negative on this side, and positive on the rod implies that the electrons from the rod must have been moved towards the cloth. Only then the rod can have deficiency of electrons, and only then cloth can have excess electrons. Which row gives the name of these particles, charged particles, and the direction in which they move? Protons, not even in the equation. We never mention, once again, we never mention this process in terms of protons. And in that case, B is the right answer. How? Because first of all, charged particles would be electrons, and the electrons would have moved from the rod towards the cloth. Right? Only then the rod can have positive charge. And how do we know that the rod must be having positive charge? Is given in the statement. It's written over here. The rod becomes positively charged. All right, it's written over here. Moving on to the next one. In the diagram, the rod R hangs from an insulating thread. Okay. When the positively charged rod Q is brought close to the rod R moves away from the rod Q. If they move away, I mean, it can move away only if the charge on the rod R is the same as the charge on the rod Q. Since the charge on the rod Q is positive, then this end of the rod, at least, or the rod R, must be having the same charge. I mean, this is the only way the rod Q would move away. Sorry, the rod R would move away from the rod Q, because of force of repulsion, and the force of repulsion exists only if these were like charges. So which conclusion can be made from this observation? Rod R is charged, but it is not possible to identify the sign of the charge. No, whenever there's movement away or towards, we can always identify the charge. So A can't be the right answer. Rod R must be positively, yeah, that makes sense. Rod R must be positively charged. Only then it would be pushed away. Only then it moves away from the rod Q. Alright, here we have another one. A student holds a rod in his hand. He rubs the rod with a cloth. The rod gains a positive charge. Of which material could the rod be made, and which transfer of charge has happened? First of all, whenever you're charging the objects with the method of friction, and I explained this thing in my previous video as well, that you must be having insulators. Matter of fact, charging by friction works only for insulators. So the material of the rod cannot be a metal are conductors, so you can throw the option A and the option B out the window. So you're left with the option C and D. And even without knowing anything, I can straight away discard the option D as well. I mean, like I said, I've stated multiple times now, in this chapter, you have to explain the charging or the movement of charge in terms of electrons, in terms of the negative particles, not in terms of protons, not in terms of the positive charge. So you'll be left with only option C. And that makes sense. Negative charge from the rod to cloth. If the negative charge from the rod, if the electrons move from the rod towards the cloth, only then the rod can have positive charge. And it was mentioned in the question, then the rod gains the positive charge. And that's the only way for rod to gain the positive charge, if the electrons from the rod move towards the cloth. But I mean, you can easily sort this out within 5 to 10 seconds with the method of elimination. First of all, you should be able to eliminate these two, because these two mention the charging, these two mention conductors, and the option D mentions positive charge or protons. So A, B, and D would be discarded straight away. You'll be left with the option C. Now moving on to the paper 2 questions. Alright everyone, so let's move on to the paper 2 questions. The first one, we have figure 7.1 shows two charged metal spheres. One sphere has a positive charge and the other sphere has a negative charge. Just let me grab my pointer from here. Yeah. Part A says, on figure 7.1, draw the electric field between the two spheres. So there's certain rules that you need to follow, and there's a minimum criteria for the number of lines that you need to draw for the oppositely charged spheres or oppositely charged objects. It is preferred that you should be having at least 3 lines in the middle and 3 lines at the back. And for the like charges, there should be at least 5 lines in the middle, 3 lines in the middle, and at least 3 lines at the back. And yeah, it kind of straightforward. So what we do is we draw a field line from positive towards the negative. So this line coming straight from the positive towards the negative, and there's another straight line which is on the edges, one here and one over here. All right, and then there has to be line from the positive towards the negative, from the positive towards the negative. And when you're drawing these lines, you need to ensure, first of all, the direction of the field lines, right, from the positive towards the negative, also from here from the positive towards the negative. Right, they don't demand too much precision, but there should not be a dramatic difference. So this line would tend to bend towards the positive, and the arrow should be towards the negative. For the negative charge, the arrows are always towards the negative, like this. And with respect to the positive, the arrows are always away from the positive. From positive, the arrows are always outward. From the negative, the arrows are always inward. And the other thing is, make sure these lines emit radially. Alright, radially in simple words mean perpendicular to that point. So if I had drawn this line, instead of like this, let's say I had drawn the line at the top, something like this. Now this line is not coming out of this region radially, it's not perpendicular to this point. So this case, if you draw it like this, it would be incorrect. The line has to be coming out radially, perpendicularly, so it should be like this. And also, I mean, I can give you an example here. If you have to draw a line on this side, so it should be perpendicular, coming out perpendicularly at this point. So you can't draw it like this. Alright, this one does not show the line coming out perpendicularly. Once again, that would be incorrect. So make sure that the line is, once it's submerging, it emerges perpendicularly, and then it does get bent. Right, the bending and everything has to be shown only once the line has come out of the surface. So that one was the first one. Then we have the second question. Figure 5.1 shows a method of producing sandpaper using static electricity. Glue is sprayed onto moving paper. The sticky paper then passes between the two plates. One of the plate is positive and the other one plate is negative. And they have mentioned over here the upper plate is negative and the lower plate is positive. There is an electric field between the plates. On the figure 5.2, draw the electric field between the two plates. Show the direction of electric field. So the electric field, the convention is the electric field is from, direction of electric field is from positive towards negative. So you can draw a uniform electric field. In that case, you have to draw at least 3 lines and should be kind of equally spaced. They're not going to measure the spacing with a ruler, but there should not be dramatic difference. Otherwise, if it's too obvious that the spacing is not uniform, then there might be deduction in the marks. So we just try to ensure that the spacing apparently looks pretty much same, and it has to be at least 3 lines. You can draw 4 5 as well. So one of the ways you can draw, you can show uniform field in the center, and if you want to show non-uniform field at the curves, you can. Otherwise, it's not compulsory. Right, it's not compulsory according to the marking scheme. So you get 2 marks, 1 mark for drawing these parallel lines and 1 mark for the arrows from positive. The arrow is from positive to negative. Grains of sand are present just below the sticky paper. Each grain of sand is a conductor of electricity. Figure 5.3 shows 2 layers of sand grains in the space between the 2 plates. Okay, and then you can see 2 layers, first layer over here and the other layer at the bottom. Explain using the ideas about the movement of charges. Movement of charge means you have to explain in terms of electron only. All right, don't be confused with it. All right, don't get trapped by it. They might have set movement of charge, but it has to be in terms of electron only. Proton is also a charge, but we don't discuss anything in terms of proton. Why the top layer of sand becomes positively charged? So what they are asking is why the top layer of the sand becomes positively charged. In every question in O level physics, if something is getting positively charged, it means electrons must be moving away from that. It must be losing the electrons. That's the only way it can have positive charge. So you write down the same thing, that electrons um, on the sand grain move towards the positive plate. So electrons from the sand grains move towards positive plate. Alright, I don't recommend you guys to write it down like this, write in full form. State why the top layer of the sand moves towards the sticky paper, and the sticky paper is on the upper side. So why the top layer of the sand moves towards the sticky layer? Now the layer of the sand, as the electrons moved away from it, it is now positively charged, and the plate, the top plate at the top, uh, with the sticky paper, that is negatively charged. So these two opposite charges, they would try to attract each other. So we say positively charged sand grains are attracted towards the negative plate. Positively Once again, for you guys, I recommend that just write the answer in proper wording instead of using these short forms. So I'm going to skip the part C that is not related to static electricity. Um, it relates to current electricity. All right, so moving on to the next question, number dash question 5. A plastic rod that is initially neutral is rubbed with a woolen cloth. So we have two bodies. The first one is a plastic rod, and that is being rubbed with a woolen cloth. After the rod is being rubbed, it is positively charged. All right, so in other words, it means electrons from the rod would have moved towards the cloth. Only then the rod can have a positive charge, and the cloth would eventually be having a negative charge. Explain in terms of the particles why the rod is now positively charged. So yeah, what we write here is uh, electrons move from a rod to cloth. What happens? State what happens to the woolen cloth. The woolen cloth gets or becomes negatively charged because it gains the electrons, so it becomes negatively charged. An uncharged conducting sphere is suspended from an insulating thread. The positive charge rod is placed near to the surface as shown in figure 5.1. An uncharged conducting, so this sphere was previously neutral. That implies it was having equal number of protons and electrons. It was having equal number of positive and negative charges. On figure 5.1, draw the distribution of the charge on the sphere. Alright, so yeah, for this one, since this rod was uncharged, uh, the charges on that one, the positive and negative, would be distributed in such a way that the negative charge would be accumulated in front of the rod because the like charges repel, and the positive charge would be accumulated on the away side. So negative charge on the left side, positive charge on the right side, but it should be equal number of positive and negative, and it has to be at least, you have to show at least 6 uh, charges in total. Explain why the sphere is pulled towards the rod. All right, and this question is for 2 marks. Now for the first one, you see, since the sphere was neutral, so there are 2 forces acting on the sphere. First one is the force of attraction, and the force of attraction is between the positive charge and this negative charge. This is a force of attraction, but at the same time there's a force of repulsion as well, and the force of repulsion is between the positive of the rod and the positive of the sphere. So positive of the rod, positive of the sphere is trying to move these 2 objects away from each other, but the positive of the rod and negative of the sphere is trying to bring these 2 objects close to each other. So there's a force of attraction, there's a force of repulsion. Which force is dominating? Obviously the force of attraction, because the negative and the positive, they are close to each other compared to positive and positive. So what we write here is the negative charge is on the rod, the negative charge on the sphere is attracted towards a positive charge of the rod, and for the second mark you have to mention this thing, and make sure whenever you're writing these answers should be consistent with the demands of the Cambridge, and this thing comes only with the practice. I mean, to be very honest, this question can be explained or answered in different ways. A lot of ways you can answer these questions, but you have to answer it in a way that it is accepted by the Cambridge. It falls on the criterias. It falls. It contains those specific terms, those key terms. So for the second pointer, we can write the distance between the negative and positive is smaller than the distance between the positive, or the same point can also be written as the force of attraction is greater than the force of repulsion. So force of attraction is greater then force of repulsion. Force of attraction between these two objects is greater than the force of repulsion. And what's the reason for that? You don't need to write it down, but the reason is because positive and negative, this positive and this negative was close to each other compared to positive and positive. So that's the end of it. If you haven't subscribed the channel, please do hit the subscribe button, and you can be waiting for more videos. That's it. See you in the next video. Take care.